Hello and welcome to this My GCSE Chemistry video about reversible reactions and equilibrium. You may have come across reversible reactions already, but they are quite unusual because a reversible reaction is one in which the products can turn back into the reactants again, i.e. it can proceed both forwards from left to right and backwards from right to left. Most reactions aren't reversible, but if a reaction is reversible, then it will have this double-headed arrow. Make sure that each arrow only has a half head and the top one is facing the right-hand side and the bottom one is facing the left-hand side. Here is an example of a reversible reaction, where heating ammonium chloride turns it into ammonia and hydrogen chloride gases. But the direction of the reversible reactions can be changed by changing the conditions. So for example, if you cool down ammonia and hydrogen chloride gas, it would form back into ammonium chloride, the original reactant. This can happen over and over again by heating the reactants or cooling the products, and the reaction will continue to proceed forwards and backwards until you stop changing the conditions. It's important to know that in every reversible reaction we have two reactions going on in opposite directions, and one of those reactions will always be exothermic, while the other one will always be the opposite, so endothermic. If you think back to the energy changes topic, if we have a negative energy change, this means it's an exothermic reaction. Positive energy change means it's an endothermic reaction. So as we said in the earlier example, if heating one side of the reaction causes the reaction to go in one direction, then cooling the other side of the reaction will cause the reaction to go in the opposite direction. This is because in a reversible reaction, the same amount of energy will be transferred, no matter whether you're going forwards from left to right or backwards from right to left. Here's another example of a common reversible reaction. We have hydrated copper sulfate on the left-hand side, which is blue. And it's blue because its crystals contain molecules of water in a particular crystal structure that reflects blue light towards our eyes. If we heat it strongly, the forces that hold the copper sulfate to the water molecules in the crystal get broken down, and the water is released as water vapour. This leaves us with anhydrous copper sulfate, that is copper sulfate with all of the water removed. That takes away its blue colour and leaves it as a white powder. However, we can reverse this reaction just by adding water. If you add a couple of drops of water to white anhydrous copper sulfate, it will turn back into hydrated copper sulfate and change colour back to blue. This can be done over and over again, changing hydrated copper sulfate into anhydrous copper sulfate. You may have already come across this as a test for water, and you'll see this again later on in the chemical analysis topic. In the examples I've given so far, the reactions go forwards and backwards, but they happen one at a time, and each time we have to change the conditions. But this isn't always the case. If we have what's called a closed system, which means the reaction is taking place in a container that's sealed so that the products cannot be released and no reactants can be added, then both the forward and backwards reactions can occur at exactly the same time. While to start with, one of the reactions might be going faster than the other one, perhaps because of the temperature in the container or the pressure. Eventually there'll come a point where the forward and the backward reaction are occurring at exactly the same rate. If they're both occurring at exactly the same rate, this means there won't be any overall change in the amount of reactants or products present. So if you're looking at the reaction from the outside, it will look like nothing's changing. But actually, both the forward and backward reactions are happening at the same time. If this is hard for you to imagine, I wonder whether you've ever tried running up a down escalator. In this picture, the girl represents the forward reaction and the down escalator represents the backward reaction. If the girl is moving up faster than the escalator is moving down, then she'll proceed forwards towards the top of the escalator. But if the escalator is moving down faster than she's moving up, then she'll end up back where she started. However, if she can run at the same speed that the escalator is coming down, then her position on the escalator will stay the same. In this case, if the girl and the escalator are moving at the same speed, this would represent a position of equilibrium, a point at which the forward and reverse reactions are occurring at exactly the same rate. That's it for this introduction to reversible reactions and equilibrium. If you're on foundation tier, that's all you need to know about it. But if you're on higher tier, I suggest you go directly onto the next video, which is for higher tier only, as that talks about the different factors that can affect a position of equilibrium and therefore how much product can be made. Thanks very much for listening. I hope you find these keywords useful and see you again soon on another video by My GCSE Science.